Hello. So this is like the fourth Zoom meeting on the chapter 2 review, and we will finish the last two questions of the chapter 2 review. And that is first question 23, here highlighted in blue. A rock with a mass of 452 grams is placed in a graduated cylinder containing 355 milliliters of water. The water level rises to 525 milliliters. What is the density of the rock in kilograms per cubic meters? So in this exercise, they are using what we call the Archimedes Principle. Maybe I can write this down. Archimedes Principle, where when you have an object that doesn't have a geometrical shape where you can measure, the shape, using a ruler or something like that, when it's a rough shape like a rock, you can use the Archimedes principle to measure the volume of the rock. And for this, you use a graduated cylinder. So it has to be big enough for the object you want to measure the volume for. And so you fill it with water, and hopefully your object doesn't dissolve in water. So it has to not dissolve in the water or any liquid that you want to use, but water is the easiest liquid to use. And so you fill it, you record the volume of water you have initially, and here it's 355 milliliters of water. And when you place the rock inside the graduated cylinder, the water level will rise. And here you have the value, 525 milliliters. So this allows you to measure the volume of the rock by taking the difference between the final volume of water and the initial volume of water. So that's how we will get the volume of the rock. So what do we have for now? We have the given here is the mass of the rock. So the mass of the rock, 452 grams. And we are given the volume of water, initial volume of water. So VI of water, 355 milliliters. Final volume of water, 525 milliliters. And so we will then calculate the volume of the rock by doing the difference between the final volume and the initial volume. And the question is asking for the density in kilograms per cubic meters. Notice how the mass of the rock is in grams and the volumes here are in milliliters. So there will be the need to change those units to match the units of the density that we want. So, and we will use the formula density equals mass over volume to calculate the density. But so let's start by collecting the data. So we have the mass of the rock, we need the volume. For the volume, we do the volume of the water when the rock is inside the cylinder minus the volume of water before. And so it's 525 minus 355 milliliters. So you get the volume of the rock, 170 milliliters. So notice how I have the dot here, because when you calculate this in the calculator, it's 170. But here we are doing a subtraction. And so we need to keep the least number of decimal places or the least precise digit. And in both volumes, we have the volumes to the ones place, to the milliliters. So we need to keep the precision to the milliliters. And that's why here we need the dot to say that the 0 is significant. So that's why we have that dot here. It's to make it 3 significant figures and keep the precision to the milliliter. So we have the mass of the rock in grams and the volume of the rock in milliliters, but we need to change them to kilograms and cubic meters. So let's convert first the mass of the rock from grams to kilograms. And this is done by simply using the equality that relates grams to kilograms. So of course, you're getting this in this document where you have the metric prefixes. 1 kilogram, and you change the kilo by its prefix, by its value, sorry, is equal to 1,000 grams. So that's why I get this 1 kilogram is 1,000 grams. And then you take your given amount, 452 grams of rock. That's in the numerator. Remember, even though it's here written like in the middle, in between, it is in the numerator. It's like having a line under and a 1 in the denominator. So start by the given amount in grams and then multiply by the conversion factor that will convert the grams into kilograms. And so we want the grams to be cancelled, the units. So we will have the grams on the bottom and then the 1 kilogram on top. This way the grams cancel and we're left with kilograms. And so it comes down to dividing 452 by 1,000, and that's 0.452 kilograms. So we've changed our mass of grams into kilograms, so that's done. Now you need to change the milliliters into cubic meters. This is more tricky here. If we look at the document here, we have an important fact, and I hope you notice it, even though it's, there on the side. There is a very important conversion equality that you want to remember using it. You need to remember that it's there. And it's 1 milliliter equals 1 cubic centimeter. And that's what allows you to go from units of liters, or milliliters to cubic centimeters or cubic meters. So that's what we will start with, because we start with milliliters. So we'll first change the milliliters to cubic centimeters. And then we will use the fact that we have 1 centimeter equals 0.01 meter. 1 centimeter is 0.01 meter. And we will raise that to the cube to make it cubic centimeters and cubic meters. So let's see how we do this. So we want first to convert the volume from milliliters, to cubic centimeters using the fact that 1 milliliter is 1 cubic centimeter. Then we need to change those cubic centimeters to cubic meters. And what we know for now is that 1 centimeter is 0.01 meter. So you need to raise this equality to the cube. And so that means doing this. You are raising both sides of the equality to the cube. So you take 1 centimeter and raise it to the cube. And you take 0.01 meters and you raise it to the cube. And when you raise to the cube, you raise everything, the units and the numbers. So then when you are doing on your calculator, 1 to the cube is still 1. Centimeter raised to the cube becomes cubic centimeters. And then 0.01 to the cube. So if you do that on your calculator, 0.01, and then you use the caret key, and then cube, so third, and it's equal to this value, 0.000001. And then the meters will become cubed because you've raised to the cube. And so if you use scientific notation, this number with a lot of zeros can be written as 1 10 to the negative 6. You can use the different display mode of your calculator. So you do second DRG, move the arrow to SCI, and then you have the same number now in scientific notation, and it's 1 10 to the negative 6 cubic meters. So we have our relationship now between cubic centimeters and cubic meters. And that's enough. this will allow us to go from milliliters to cubic meters. So let's see how we do the conversion now. Yeah, the roadmap here shows that how we will go from milliliters to cubic centimeters to cubic meters. So let's do the calculation. So we start with the given amount, and here the given amount is the volume of the rock in milliliters. So let's type this 170 milliliters. That's a simple measurement here, and so in the denominator it's a 1, right? There is no per something, per hour or per second or things like that. So it's a 1 in the denominator. Remember how this is in the numerator. The given amount is always in the numerator. And then we will multiply by the first conversion factor that will change the milliliters to cubic centimeters. And because we have milliliters in the numerator, we want the 1 milliliter in the numerator, in the denominator, sorry, so that they cancel the units. And then the 1 cubic centimeter in the numerator. And we need this cubed. So that changes the 170 milliliters to cubic centimeters. And next, we need to do the cubic centimeters to cubic meters using this equality here. So I will use the scientific notation. And because we have cubic centimeters in the numerator, we want the cubic centimeters in the denominator. So 1 cubic centimeter, and it's 1, right? 1 cubic centimeter is equal to 1 times 10, and we need to format this, 10 to the negative 6. And the unit of that is meter cubed. Okay, so this is this equality, changed into a conversion factor such that we cancel the units of cubic centimeters and we are left with cubic meters. So the answer will be in cubic meters because we have canceled the milliliters and the cubic centimeters. In the calculator, you do 170 times 1, second EE key to get the capital E, and then you just put the exponent of negative 6, and you get 1.7. Remember, I forgot, but here we should see the dot for the milliliters, right? Remember we said we need to keep to the precision to the 1 milliliter. So the calculator answer is that, but we need to add the 0 to keep the number of sig figs here. 3 sig figs in 170. All the other numbers are exact numbers. It's by definition that 1 milliliter is equal to 1 cubic centimeter, and by definition also between the cubic centimeters and cubic meters. So it's that, and then times 10 to the power of negative 6. Negative 6 meters. Okay, so that is the volume with the proper number of sig figs in cubic meters. So we have now our volume in cubic meters and we have our mass in kilograms. So we can now calculate the density in kilograms per cubic meters. So let's calculate then the density. So density is mass over volume. So the mass, we said 0.425 kilograms over, let me copy that. Here, 1.70 times 10 to the negative 6 cubic meters. And you can see here that the unit will be in cubic meters. Let me prepare that the unit is kilograms per cubic meters. And so that's a bit big. Okay, well. So let's do the calculation. 0.425 divided by 1.70 times, so 10, or second EE key, -6. And here it is important to use the scientific notation because you are dividing by 1.70 10 to the -6. If you do not use the scientific notation, what some calculators do is that they will move the times 10 to the -6 up to the numerator if you don't use a parenthesis around this whole thing. So using the scientific notation in your calculator will guarantee that it takes it as one number and keeps everything in the denominator. And so the value is 2.6588, etc. I think that's enough. There is more digits, but we need to round this properly. And according to the, what we had to begin with, we had 3 sig figs in the mass, and here we have 3 sig figs in the volume, and we retrieve that 3 sig figs in the mass, 3 sig figs in the volume. So we need to keep 3 sig figs. So we'll keep the 2.65. What comes after the 5 is the 8. So you need to round the 5 up to a 6. And then again, the unit of kilograms per cubic meters. There you go. So that's the density in kilograms per cubic meters. And so what you need to expect when you have kilograms per cubic meters, because, versus, grams per milliliters or versus grams per cubic centimeters, it should be a number very similar to what you would have in grams per cubic centimeters, because the, well, actually, maybe not. Maybe I'm saying wrong things here. So anyway, that's how you should do and calculate the density. Actually, I made a mistake in the volume here when I recorded the volume, when I calculated it, 170 times 110 to the -6. Here we are moving the decimal point 2 times to the left when we are doing the scientific notation. So it's not 10 to the 6 here, but 10 to the -4. And if you verify that with your calculator, you will see that. So it's 1.70 10 to the -4 cubic meters. And so that will change here the value here. So when you do the density, it's going to be 0.452 divided by 1.70 10 to the -4. And yes, my value then changes a lot. By 2 places. You move the decimal point here, actually 3 places. So it goes to, instead it is 2,658.8 kilograms per cubic meter. And so let's change then the final answer with the correct sig figs. So we need to keep 3 sig figs. So the 2, the 6, the 5, what comes after the 5 is the 8. So we need to round it up to a 6, and then it's a 0. So it's 2,660 kilograms per cubic meter. Yes, that's what I thought, that the densities, when they are in kilograms per cubic meters, usually are numbers in the thousands. So that's why I found this weird. So sorry about that. Please make sure you get the correct value here. So question 24 now. A 75.0 gram sample of copper is placed into a graduated cylinder containing 50 milliliters of water. To what volume in milliliters will the water rise to? And you're provided the copper density, and it's 8.96 grams per cubic centimeters. So let's mention that this is a standard unit for solids of, density of solids, more than the kilograms per cubic meters. So we need to find the volume to which the water will rise once you drop this sample of copper into the graduated cylinder. And we have the copper density. So we know we will need to use the density, and the density is the mass over the volume. So from the density, we can get the volume of the copper, right? Because we have the density and we have the mass. We have the mass, and now if we find the volume, then we will know how much volume the water will have moved up to because of the piece of copper in the water. So we need to change the formula of the density so that we have volume equals, so we need to solve for volume. And so, from this first formula, if you multiply both sides by the volume, then you will get density times volume equals the mass, right? Mass will be by itself here because you multiply by volume and divide by volume. And then from here, from the mass equals the density times volume, to get the volume by itself, you divide both sides by the density. So dividing both sides by the density will land to this. The volume will be by itself because you divide by density here. And it will be mass over the density. So volume equals mass over density. So using this formula, we can get the volume of the copper metal here, of that piece here of 75 grams. So we have the mass and we have the density. So it's just a matter of plugging in the value. So here first, let's say that, then the final volume of water will be obtained by taking the initial volume of water and then adding that volume of copper that we will get. Oh, yeah, I forgot. One thing is that the volume of the water is in milliliters. And when we will calculate the volume of the sample of copper, it will be in cubic centimeters, right? Because here density is in cubic centimeters. So that means the volume will be calculated in cubic centimeters. So we will need to change the volume from cubic centimeters to milliliters. And we will use the fact that 1 milliliter is equal to 1 cubic centimeter. So let's find the volume of the piece of copper. And so volume of copper is the mass of copper, and that's 75.0 grams over the density value, and the value of the density is 8.96 grams. So let me have this properly, grams per cubic centimeters. So the way that the cubic centimeters are now, they are in the denominator of the denominator, right? Grams here are in the numerator. These grams are in the denominator. They cancel. And then the cubic centimeters here are in the denominator of the denominator. So it is like being in the numerator. So that's why the final unit will be in cubic centimeters. And that's a unit of volume, and that's what you would expect. So that confirms here that the unit is correct. Grams cancel, cubic centimeters move up to the numerator. And then for the value, you do 75.0 divided by 8.96, and that's 8.37 0.5, that's enough for the calculator answer. And so we need to run this properly given the values we have. We have 3 sig figs in the mass. You know, the 0 is significant here because we see the decimal point. 3 sig figs in the density, so we need to keep 3 sig figs. So it's going to be 8.37. What comes after the 7 is a 0, so you keep the 7 as 7. And that's, and that's cubic centimeters. So that's the volume in cubic centimeters. But as we reminded here, the fact that 1 cubic centimeter equals 1 milliliter, so we can already write that it is also 8.37 milliliters. So then we have now the volume of the copper in milliliters. And so once you drop that piece of copper into the 50 milliliters of water, then the water level will rise by this value, right? So to get the final volume of water, you take the initial volume of water, so 50 milliliters, plus the volume of copper we just calculated. So it looks like this. We have the final volume of water is the initial volume of water plus the volume of copper. Initial volume of water is 50 milliliters plus volume of copper we just calculated, 8.37 milliliters. And that's then 58.37 milliliters. So when you're adding here, notice how we are adding. The rule is to keep the least precise digit or the least number of decimal places. And here the least number of decimal places is 1 in the 50.0. Here there is 2 decimal places. So let's keep 1 decimal place. So 58.3, 1 decimal place. But what comes after the 3 is a 7. So you need to run the 3 into a 4 milliliters. So that is the final answer. The final volume of water is 58.4 milliliters. Hello. Oh. Oh boy.